ME 5.09. I was unable to attend the introduction class. I think you had it last week, right? So, but let's get started. Maybe I would like to know where all you are from. And I think one of you told that some of you are from Mahindra.
Yeah, sir.
Right.
Sir, 23 batch, we have 18 people, and rest of the people, 5 people are there.
Okay.
And
So Mahindra, from Mahindra, how many of you?
right now, 18 plus this batch, this year batch around 18 plus 4. 4 or
22.
5? 22, sir. 22
from Mahindra. Okay.
Yes.
And the others, can you please at least one from each company, if you can speak?
Sir, I am Roshan Kumar. We are from Bajaj Auto. I am from Bajaj Auto. With
Acha.
me, we have 2 people like I and Vikas Paul.
Okay, 2 of you. Okay,
Yes, sir.
that makes it 24. Okay. Thank you. Thank you,
you,
Mr. Roshan.
Hello,
sir.
good evening.
Good evening.
This is Abhijit. I'm working at TVS
Yes.
Motors.
TVS Motors. Okay.
Yes.
Yeah. 25.
I'm Arun Chibakumar from Caterpillar.
Okay. Hi, Arun. 26.
Hello, sir. Good evening. My name is Amit, and I'm from Continental.
Okay. Okay. So you are alone from the company?
Yes, sir. I'm placed in Bangalore, and I'm alone from my company as of
Okay.
now.
Okay. 27 then.
Yeah, hello sir.
Hi.
Yeah, myself Vaibhav. I work for Mercedes-Benz in Bangalore.
Okay. And how many of you from?
No, I'm the single
You're
student.
alone. Okay. So we have 5 more students.
Hi sir, this is Rahul. So I'm from ZF Commercial Vehicle Control Systems in Chennai.
Okay. Okay. Yeah.
Hello, sir. This is Sri Sairam. So I'm from Daimler Truck Innovation Center, India, Bangalore. So myself and Pradeep Kumar. So both are from the same company.
Okay. Okay. I think, yeah. Thanks.
Hello, sir. Good evening. I'm Joel. I am working in Bosch, placed in Pune.
33, I think. One more.
Hi, sir. This is Chandranath from Mahindra & Mahindra, Chennai.
Yeah.
Hello, sir. This is
Yeah.
Balaji. I'm from Bosch, Coimbatore.
Okay. Okay. Yeah, I just want to know, I mean, the different organization you all are from. Earlier years, we used to have the class representative. I don't know whether there was any discussion in the introduction class.
There are 2 batches here, sir. 23 batch and 24 batch.
Right.
For the 23 batch, we have Arunachalam from.
Okay. So Arunachalam from Mahindra, right?
Yeah.
Okay. So Arunachalam is one of the class representatives for 23 batch. And
Yes, sir.
for 24? Any of you want to come forward?
No, sir, we'll come back. Sir.
Yeah, so you discuss among yourself, and maybe you can just propose one name, and you can intimate this class maybe tomorrow or this week. Okay, so yeah, thanks to all for the introduction. So before we move forward with the course, I need to talk about a few things. Let me share my screen. Right. Is the screen visible to you?
Sir.
Yes, sir.
Yes, sir.
It's visible to you all now, right?
Yes, sir. Yes, sir.
Yes. Yeah. Okay. Yes. So I just wanted to talk through the syllabus and books and the evaluation scheme. So as you know, it is ME 5109, measurement in thermal engineering. So we would be meeting Monday, Tuesday, Wednesday, 6 p.m. to 6:50 p.m. That is typical 50 minutes is the class duration at IIT Madras. So talking about the syllabus, I would just briefly talk about what all we'll be dealing with in this course. First, a couple of classes, we are going to talk about a brief introduction to measurements. And a good part of the course would involve analysis of experimental data, right? When you do some measurement, you get data, and so how do you make sense out of the data, right? So we talk about errors, uncertainty, propagation of uncertainty, few different kinds of statistical analysis to deal with experimental data, and how can we really get sort of curve fitting out of experimental data. So that would involve, I mean, we would basically take some examples, some dummy data points, and work through the different methods, and that way we will be knowing how to handle experimental data. Very briefly, we'll talk about the design of experiments. We'll also spend some time talking about orders of systems. When you deal with experimental systems, it is important to know what is the order of the system that we talk about. Is it a zeroth order system or a first order system or a second order system? Because our analysis would depend on the type of the order of the system that we deal with. And then we move on to measurement of various parameters, various quantities, mainly measurement of temperature, measurement of pressure, measurement of volume flow rate, velocity, and various thermophysical properties. And in each case, we will be talking about the theory, the principles based on which the different variables are measured. Like, for example, if you talk about measurement of temperature, you need to understand the principle of thermometry, right? How resistance temperature detectors operate, how thermocouples operate, what the principles govern working of thermocouples, different sensors, and so on, right? And we talk about in each case different kinds of measurement system, like different types of temperature measurement systems. Similarly, in pressure, we talk about various different kinds of instruments that are available to measure pressure, and same for flow rate, velocity, and the thermophysical properties. In thermophysical properties, we basically talk about viscosity, thermal conductivity, and thermal diffusivity, and so on. And the course will end with some kind of laser diagnostic measurements using laser Doppler anemometry and particle image velocimetry. So you can see that the syllabus is structured in a way that it will give you a good mix of fundamentals of different kinds of measurements, and also understanding of the actual system or device or that apparatus that are used to carry out different parameters. So talking about books, and there are two textbooks that we would be following. The first one is by S.P. Venkatesan, who used to be a professor at IIT Madras, and the book name is Mechanical Measurements. And the second one is J.P. Holman, and the book title is Experimental Methods for Engineers. So these two will be very closely following. But apart from that, there are some reference books that you may look at if you want to, if you're interested in any specific section of the course. Like J.R. Taylor, for example, deals with error analysis extensively. Dublin deals with measurement systems, and Beckwith is again a sort of a generic textbook kind of material, but we don't use it as textbook because it's very vast. But you can also refer Beckwith. So as far as the evaluation is concerned, it is pretty simple. We have a mid-sem exam, which we would announce well ahead of time, but typically it is somewhere middle of the course, right? I mean, if let's say we deal with 40 lectures, somewhere around 18, 20, 22 lectures, we will have the mid-semester exam around the middle, and that would carry 40 marks, and the end-sem would carry 60 marks, right? So if you do well in the mid-sem exam, you should continue and do well in the end-sem as well. But let's say if you sort of lag behind, but you will have an opportunity to compensate in the end-sem exam as well. So this is how we have been evaluating for last a few times I have offered. I mean, in fact, this is something that we have been following in general for this course. So that's all, a brief background of the course and evaluation pattern. If you have any question at this stage, please feel free to ask.
Professor sir,
yeah,
for mid-sem 40 marks will be conducted up to some 20 or 22 classes. Then for end-sem, the whole syllabus is considered, or post to the 23 or 24th class?
Yeah, that's a very good question. I think in IIT system, the thing is, mid-sem exam is conducted based on the syllabus that we cover till the day before the exam. Okay.
Right, sir.
And the end-sem covers the entire course.
Okay.
Yeah.
Sir, any assignment or some?
I mean, in the previous years, what I have done, and I would also like to do the same, maybe a couple of weeks before the mid-sem exam, I would give an assignment. So that would be more of sort of, so you get an idea about what kind of questions that you would expect, and you would also practice the question. You don't have to submit. You can solve yourself, because I will not be evaluating the assignments, but that will give you some practice. Of course, during the theory course, classes, we will also solve some questions. But in addition to that, I would give some assignments for your practice. And same before the end-sem. I mean, there is second assignment I will be giving for your practice, but will not be evaluating assignments.
Okay, sir. Thank you.
Professor sir.
Yeah.
Am I audible?
Yes, you are audible.
Just one query on the norms of the class, whether we can ask doubts in between, or it's better to keep our doubts to the end of the class.
I got it. I'm flexible. I think it is better that you can stop me in between while we are discussing, so that the doubt gets cleared there and then. But you are also welcome to ask a question at the end.
Yeah, noted, sir. Thank you.
Sir, I had a question.
Yeah.
So these textbooks, is there any online library as such from where we can access them, or must we refer them at our own?
See, these textbooks, I mean, they're not very expensive as far as I know. And these are available in even Amazon will have it. Not sure about online copy of this. So please have a look yourself.
Sir, out of these two textbooks, which one is preferable from you?
I said both are important. The first one is an Indian author, and second one, I mean, both should be available, I think, Amazon or at a bookstore. I don't have any preference as such on any of these two. I would be referring material, I mean, from both the books, actually.
Okay. Sir, will you be sharing the slides, or we have to make the note and like?
Yeah,
Of course we'll make the
so
notes.
as you see this course, that's a good point. What I normally do, and that I also plan to do this time, is starting from 1 till 3. Okay, 3 I would be doing on the notepad, and you have to take notes. Okay, and but 4 onwards I will be teaching on slides, so that I can share with you. Okay, you want, I mean, particularly the number 2 involves a lot of I mean, sort of different methods. I mean, it is more mathematical. Okay, so I mean, it doesn't make sense to just read from slides. So we can work through that, will give you some better understanding of the topics. But 4 onwards, I normally do it on slide because there are many figures and schematics, images. So, I mean, it is more convenient on slides. And I mean, there is less math, more of discussion. But yeah, 1, 2, 3 will be, you have to take notes from my screen. And then remaining I'll be doing on slides. But if you, let's say you miss a class, I mean, what I do is I also save it, and so that, I mean, if you miss and if you have a valid reason why you missed the class, then I share the notes with you.
So thank you so much.
Professor, will there be any lectures for this?
Sorry, can you repeat?
For this course,
I missed your point. Can you?
No, sir. Any lab practical classes are for this subject, sir?
See, the thing is, we did, I mean, in the beginning, I think once, but it was very difficult to coordinate, particularly, you know, since you are not in station. So later years we have been focusing on theory only. So this year we will also do the same.
Okay, sir. Okay.
Sir, for future reference, we will have. Shall we have? Can we have the recorded videos of the lectures, or
yeah? So I mean, this is something that we have been debating in the department. So what we have concluded, and I mean, particularly for this course, as I said, we would like students to attend. I think it is really good for you. Although, I mean, you take classes after your office hours, and I teach after my office hours. But I think it is better for you that you attend. And let's say due to some valid reason you are not able to attend. I mean, I just said I am ready to share my notes. Of course, you can get it from your colleagues and friends also. But I feel that, I mean, if we do that, recording may not be needed. But if you have, let's say, some doubts, and you can, you know, contact me. I am ready to explain to you, and then, you know, help you with whatever is required. So I hope you get the answer.
Yes, sir. Yes, sir. Thank you, sir. Thank you so much.
Hello, sir. Good evening.
Yeah.
This previous point you mentioned that lab used to have, but because of convenience or travel, you're not having this year. But if you plan to have, I would be willing to attend that. That's.
Yeah,
or
I would
which-
have to check with the department because, see, mainly, the thing is, the class is, you are basically physically not present in the campus. So there are logistic issues. We have faced issues in earlier, some 5 years back, we did once. And then I think after that, it was decided to keep it a theoretical course. So, but if that is possible at all, I'll be also happy to accommodate and I will inform you accordingly.
Right. Thank you.
Right. Mm,
Excuse me, sir.
yeah.
Sir, some of us are not stationed in Chennai, right? So basically for mid-sem and end-sem, we in our last semesters, we used to attend mid-sem from the city where we are in. Whereas for end semester, we used to attend at IIT. So are we going to continue the same or there is something?
Let me check about that. Let me not commit to you at this point of time. See, during COVID, we have also done both midterm and end-sem online. I mean, it was very, very difficult, but we have done that. But now that things are normal, I really need to, take your request to the concerned person who should be able to decide and tell us. I mean, as I understand, you would prefer that midterm you would write from your company, and then for NSEM you would want to come here, right? But
Yes, sir.
whether that is something that IIT Madras would agree to, I would have to check that and I'll get back to you.
Okay, sir. Thank you.
But one thing for sure is that we would announce it well ahead of time so that in case if you have to come, let's say if they prefer it that way, I would make sure that you know the date well ahead of time. Okay, but writing from there, I have to check.
Okay, sir.
Any other question before we get into the course?
Sir, regarding the exams,
Yeah.
you just mentioned the tentative schedule, but is there any calendar of sorts available that we can use to keep track of? Because
Yes.
the website,
So normally our code office shares with us a detailed calendar. I know exact date, day of the midterm and some everything, but this year it hasn't come. I would check with them. They may be working on it. But in fact, they would also include holidays and everything, and they'll send us a calendar. This year it hasn't come, so I need to check with them.
yes, sir, because the website, what they shared with us, where we can log in and access all the course content, has a link to add calendar, but it isn't leading anywhere.
Yeah, actually earlier they were sharing with us an Excel sheet. I mean, where all the class details are there, including holidays and midterm and same. But this time nothing has come. I'll have to check with them.
Hello, sir. Just
Yeah.
another point. As you showed the syllabus just before, so is there any place where we can download some such kind of stuff?
You mean to say the syllabus?
Yeah, syllabus or
Syllabus
anything
I can
related to it.
share with you. I think what I can do is I will have a Google Drive link. Okay. And there I will upload the syllabus and I will share that link with you. And probably we'll use the same link when I upload, let's say the class materials and the slides, etc.
Right.
We'll do that.
Thank you.
Sir, may I request you for introducing yourself, sir, a bit? I'm sorry.
Sorry, I didn't get that. Can you?
Sir, can you introduce yourself, sir, a bit? Like what I mean to say is a basic thing about yourself, sir. I'm sorry.
Yeah,
If
yeah, I would do that. So my name is Ashish Kumar Sen. Okay, I am a professor in the Department of Mechanical Engineering. I have been a faculty here last, I think, 14 years now. And so initially I joined as an assistant professor, then associate, and I have been a full professor since 2021. I did my BTech from NIT Rourkela and my master's from IISc and PhD from USC Columbia. And after that, I was working in industry for some time in the UK and also subsequently with an UK university before I joined IIT Madras. So here I'm an experimentalist. I do experimental research. So we develop devices and systems for healthcare diagnostics. So that is where my research focus is. So we do a lot of fundamental research also, looking at mainly fluidic and thermal aspects of different flow situations and design of devices, systems, and so on. And we try to apply that understanding for development of these devices and systems mainly for, as I said, healthcare diagnostic application. So yeah, that's my background, and my focus is really on, as I said, experiments. So I have been teaching the measurement in thermal engineering course several times because it's very close to what you actually do in your research, experiments, measurements. And so yeah, I mean, that's pretty much about it. But if you have any specific questions, feel free.
thank you so much, sir. That was really nice to know.
Right. So as I said, so today's class, I would try to introduce you to measurement. Let me write here. Are you able to see my text that I'm writing?
Right, sir. It's visible.
Yes, sir. Yes, sir.
Okay. So if you talk about, let's say, science, engineering, and technology, these are actually based on 3 pillars. Okay, one is theoretical analytical modeling, theoretical or analytical modeling. Second one is numerical simulations. And third one is experiments. So what I mean by when I say 3 pillars based on which science, engineering, technology is based upon. For example, let's say you would have, if you are from mechanical engineering, you would have studied, let's say, flow through a tube, right? And you know that when fluid flows through a tube, there is typically a parabolic velocity profile that develops within the tube. The velocity of the fluid is 0 at the wall, which you call the no slip condition, and velocity of the fluid is maximum at the center line, right? So this is a scenario and you are trying to understand the behavior of flow, right? How do you understand? Let's say you want to understand through theoretical or analytical modeling. So what is your approach? Typically, the approach that you take is that you need to identify the set of equations that govern this flow phenomena. Namely, in this case, if you are aware of Navier-Stokes equation, and then you, of course, solving Navier-Stokes equation for a flow-through tube is incredibly complex unless you make certain assumptions. For example, you assume that flow is incompressible, flow is steady and uniform, and so on. And with these set of assumptions, you simplify the Navier-Stokes equation and you bring it to a form where you can apply boundary conditions and get an expression for velocity profile, right? So if you go back to your fluid mechanics course that you would have taken during your master's or BTech, that is what you do, right? You do analytical modeling, theoretical modeling of a particular situation, in this case, the flow scenario, and you get a solution for a velocity profile. Okay, how velocity varies at different points across a section of the tube, right? So that is one approach. In theoretical analytical modeling, typically the general guideline is that you first look for the governing equations, the set of mathematical equations that can depict this particular phenomenon, and you try to simplify to bring it to a form where you can analytically, you can derive using pen and paper how in this case, how the velocity varies in, let's say you have a heat transfer problem, how the temperature varies or how pressure varies and so on, right? So this is theoretical and analytical modeling. Then the second approach is numerical simulation. So if you work, let's say in aerodynamics, right, you want to predict drag over a, let's say, car, right? So the car is moving at some velocity and you want to estimate what is the drag force experienced by the car. So it is extremely difficult to predict this from theoretical or analytical modeling, right? You resort to what is called numerical simulation, right? So you create three-dimensional geometry of the car using some, CFD, computational fluid dynamics software, and you apply the boundary conditions. Okay, this is air. Air is flowing at this velocity. This is the viscosity, density. These are the properties of the medium, which is air. And then you find out the pressure difference, pressure profile through different sections of the car, and you integrate to get the net pressure difference, and you find out the drag, right? So this is how you get, let's say, total drag experienced by a vehicle as it is moving at some velocity in the air, right? So you do that through numerical simulation. So as I said, you have to use some kind of computational fluid dynamics software. So what does it do, right? A software basically solves a set of equations similar to, what you deal with in theoretical analytical modeling approach. But these equations are not solved in pen and paper. They are discretized using different methods like finite volume method, finite difference method, finite element method. They are discretized and with appropriate boundary conditions, initial conditions, these are solved on a powerful computer. And then you get your flow field, temperature field, velocity field, and so on, right? So this is the second approach whereby you use some kind of numerical scheme. You use powerful computers to get the solutions. Okay, this is called the numerical simulation. The third approach is experiments, right? And Experiment, as we know, gives a clear picture, right? For example, if you want to know how much is the drag experienced by the car, unless and until you actually do some experiment and validate at least some of the parameters with that you get from your simulation, it is very difficult to believe only numerical simulation or theoretical results, right? Because there are certain assumptions that you make in theoretical modeling. Like, as I said, you say steady flow, incompressible flow, uniform flow. Same set of approximations you also made in numerical simulations. You also use some discretization technique, and each discretization technique would involve some error. So you won't basically know the accuracy of neither theoretical analysis or numerical simulation results unless and until you actually do experiments and validate your analytical and numerical results. So in experiment, you actually test the real system or the process, right? And in experiments, what you actually do in experiments? In experiments, you actually measure various physical parameters, right? In experiments, you measure physical parameters. So in that context, measurement comes in, right? When you talk about measurement, you are basically doing experiments and you are measuring some physical parameters. Now, how do we define measurement? Right? What is measurement? Let's say if somebody asks, you have taken a course on measurement in thermal engineering, what is measurement? So how do you define measurement? There are different ways you can define measurement. The way, one of the ways that you can define measurement is that for sure measurement is a process, and it is a process that you use to obtain meaningful data to understand and characterize a system or a process, right? So measurement, to talk about measurement is a process used to obtain meaningful data to understand and characterize a system. Okay, so for example, you talk about let's say a computer. Let's say you take the example of the computer, and there is a cooling system inside the computer, right? Typically, inside most computers, for cooling the processors, you have this heatsink and fan, right? So let's say you want to measure, you want to perform measurement to sort of design a CPU cooling unit. Okay. So what are the measurements that you do? Typically, somebody who designs a CPU cooling unit would talk about 3 different requirements. Okay, so for example, it should maintain the temperature within certain prescribed limit, something like maybe depending on the processor, 80 degrees centigrade, 70 degrees centigrade, and so on. The second requirement will be how much noise, let's say, can you tolerate? Let's say you put a powerful fan, it will really cool down the chip, but it'll make a lot of noise that nobody likes, right? So you'd have some restriction on how many decibels of noise the fan would, the heatsink fan would emit. And there are also requirements in terms of shock and vibration, right? Typically, these computer systems, let's say they are on mobile platforms, something that is moving and undergoing vibration. These systems should be sturdy enough to be able to perform in those conditions. So typically they do thermal test, then sound test, and the shock and vibration test. So to be able to design, you basically have to do measurements, right? So you are basically measuring temperature, measuring sound level, and measuring, let's say, the vibration level, right? So you are basically using these measurement as processes to obtain meaningful data. Meaningful data is very important, meaning you have to get temperature data, you have to get sound level data, and you have to get the vibration level data, right? And through this data, you are basically understanding this system, which is the CPU cooling system, and you are also characterizing system, how good it is. Let's say you increase the input power to the processor. How is the temperature changing? Okay, is it still within the allowable limit? Or if you change the heat input, the input to the fan, it is also increasing, right? How much the RPM of the fan has to increase. So through measurement, you would be able to not only understand, but also characterize systems. Okay. So knowing what measurement is, and we must understand why do we measure? We said we measure. Why do we measure? So there are few reasons why we measure. The first is if you want to explain new observations. Okay, let's say you are doing your day-to-day work, and you are doing, let's say, some experiments, and you suddenly observe something that is not that you observe every day, or something that is surprising or something new. So, for example, let's say something non-intuitive, right? So you have to do set of measurements to actually explain new observations. Why did you observe that, right? So you do measurement sometime is to explain new observations. And that is to understand physical systems. Okay. Let's say you are, putting a drop of liquid on a surface, and you suddenly observe that the drop basically bounces and flies, right? So this is a very non-intuitive phenomenon, right? You don't expect this to happen in day-to-day life. Typically, drops fall on surface and they spread or get observed. But let's say a drop falls and just bounces like a ball, right? You would get surprised, and you have to now do measurements to explain these new observations. For example, what is the property of the liquid, right? What is the interfacial property of the liquid? What is the density of the liquid? What is the viscosity of the liquid? What kind of surface it is? What is the roughness of the surface? What is the stiffness of the surface? You do a lot of measurement, right? To explain these new observations that you just made, right? And that will basically enhance your understanding of physical system. You also do measurement to validate an established theory or propose a new theory, right? You want to validate an established theory or propose a new theory. Right? For example, you know Hooke's law, right? You take a spring and you apply load, and your deformation is proportional to the load. And this is a theory that you have learned from your school and so on. But you can do measurement. You can measure the elongation, and you know that, okay, for a certain load, this is the elongation that you expect theoretically, but you do measurement and try to validate the established theory. Or propose a new theory, right? For example, let's say you develop a new kind of material, right? And let's say upon subjecting to strain or elongation, let's say the stiffness of the material increases, right? So there you will see that the elongation is no longer proportional to the load. The elongation doesn't follow a linear pattern characteristics, right? It becomes nonlinear, right? So it's a new kind of material. So you propose a new theory to support your observation. And the third and the most important thing why you do measurement is to generate data for design of a system or process. Generate data for design of a system or process. Okay. For example, I said about this cooling system, design of a cooling system for a CPU, right? You have to do a lot of measurement. You have to generate temperature, sound, and vibration data to be able to design a good cooling system, right? So these are three different reasons why we do measure. Okay. Now, knowing why do we measure, can we look at different measurement categories, right? So we look at the measurement categories. Based on what we measure, we can actually categorize the measurement into primary quantities and derived quantities. Primary quantities and what are primary quantities? Primary quantities are those that are, so this is directly measured using an instrument. What can you measure directly using an instrument? You can, for example, measure mass. You can measure length. You can measure, for example, temperature. You can measure mass using a weighing balance, right? So you measure mass using a weighing balance. You can measure length using, let's say, a scale. You can measure, let's say, temperature using a thermocouple, for example, or a thermometer. You can measure power using a power meter. Okay, acceleration, accelerometer, pressure using a manometer. So these are parameters, quantities that are directly measurable using an instrument. So you have an instrument, you stick it in, and you measure what mass is, length is, temperature is, and power is, right? Then you have derived quantities. So derived quantities are not directly measurable. So you basically measure two or more primary quantities, and then you reduce the derived quantity from there. Okay. For example, let's say, so this is basically estimated, not directly measured, estimated by measuring two or more primary quantities. Okay. So for example, you want to measure, let's say, if you in heat transfer, right, you talk about Nusselt number, right? Nusselt's number. Nusselt's number. Nusselt number is a function of Reynolds number and Prandtl number, right? Let's say this Nusselt number is a derived quantity. So you have to know Reynolds number, you have to know Prandtl number. To know Reynolds number, you have to have mu UL over rho UL over mu, and Prandtl number is Cp mu over K. So you see that you have to measure density, velocity, length, dynamic viscosity, specific heat, and viscosity, and you have to measure thermal conductivity. So many quantities you have to actually measure to find this Nusselt number. Okay. So a simple derived quantity will be, let's say, you want to measure velocity, for example, right? So in simple case, you cannot measure velocity using a single instrument, right? A single instrument you can use to measure, let's say, distance and time, maybe a clock, a scale and a clock, and you want to measure velocity, right? For example, if you put a metal ball into a fluid, right, and you want to measure at what velocity the metal ball is falling down inside the fluid. So you don't have any instrument directly to give you the velocity, right? You have a scale and you have a clock, and you say at t equal to 0, this is where the ball is, and at some t equal to 5 seconds, the ball is here. So you measure the length, you measure the time, and from there you basically predict what is the velocity. So the simple example would be velocity, which is obtained by measuring length and time. So you have an instrument to measure length, you have an instrument to measure time, and then you basically predict what is the velocity. So this is an example of derived quantity that is not directly measurable using an instrument, but by measuring primary quantities, you are able to. Just one more thing before we stop. Now you can also have measurement categories based on how you measure. Okay, based on how you measure. So based on how you measure, you can actually divide into non-intrusive method, and intrusive method. So first, let us talk about intrusive method. Okay, first let us talk about intrusive methods. Let's say you have a pipe and you want to measure the velocity. So you use typically pitot tube to measure velocity. So you put a tube and you basically have stagnation point there, and you equate the total pressure, the stagnation pressure, and the static pressure, and you measure the flow velocity of the flow. But the thing is, when you put in the pitot tube into the pipe, you basically obstruct some area of the flow of the pipe. Essentially, the velocity, as you know, that velocity is basically flow rate divided by area. Now, if this flow rate is constant, let's say you have a pump which is driving this flow, and now when you have put in this pitot tube, the area has reduced, right? Flow rate is constant, area has reduced. That means the velocity will increase, right? If the pitot tube is the length is or the dimensions are significant, what it will measure is basically an increased velocity, because presence of the pitot tube has now reduced the area. So your velocity is going to increase. So this is an intrusive method. That means by putting a particular instrument, it has changed the original flow field, right? And what you measure is actually a velocity which is higher than what it really is. So when a measuring instrument is influencing the original measured quantity in the process of measuring it, it is known as intrusive method. Let's say you want to measure temperature of a surface, right? And put in a thermocouple. Thermocouple is a material, it's a metal, so it will conduct heat. And there is some cooling effect because of that, right? So actual temperature, the temperature measured by the thermocouple becomes less than the actual temperature, right? So then it is called an intrusive method. The instrument perturbs the original measured field, measurement field. But in non-intrusive methods, the presence of the instrument doesn't affect the original measurement field. For example, same velocity measurement, but you do not put in a pitot tube. Instead, you use, for example, laser Doppler velocimeter. Laser Doppler velocimetry basically doesn't put any physical probe into the system. There are optical light beams which intersect somewhere in the flow field at the point that you want interested to measure velocity. And depending on the shift in the frequency using an interferometer, you basically predict what is the velocity. The shift in the frequency is proportional to velocity. Now, light beam doesn't really perturb the flow field, right? You are not really physically blocking or changing the flow field. So same velocity measurement using a laser Doppler velocimeter is an example of non-intrusive method. Okay, because in this case, the instrument doesn't alter the original measurement system or measurement field. Okay, so but as I said, this is not really very strict, because if you, let's say the tube, this pipe is several meters in diameter and the pitot tube is, let's say, few millimeter, the obstruction is negligible, right? And even if you are putting a physical system, you can still treat this as non-intrusive because the change the physical intrusion makes is quite negligible. Okay. So depending on the scenario, when this pitot tube velocity measurement method can be treated as non-intrusive. Okay. But at the same time, if you take laser Doppler velocimetry, you are dealing with optical beam. Let's say you are using some laser, right? And high power laser, let's say, and let's say the fluid that is there inside is sensitive to light, right? Even if you are not physically putting something, you are putting light beam, but the light beam, let's say, is modifying the fluid property. Let's say the fluid itself is light sensitive fluid. So even in that scenario, even if you are not even if you are not putting anything physical, even with light beam, you cannot tell that this method is non-intrusive because it is modifying the measurement system. The light is modifying the fluid property. Okay, so it's really, the particular, depending on the situation and the measurement method, you tell that whether your measurement is intrusive or non-intrusive. If it is non-intrusive, you don't need to correct for that. You correct your data that is coming out of measurement. But if it is intrusive, then you need to correct your data depending on the level of intrusion. Okay, so with that, I would stop here. And if you have any question, you can ask.
Sir, am I audible?
Yeah,
Just a small query on that pitot tube example.
yeah.
You can extend your answer for the other part of the question, but point is whether we will put any extra coefficients to compensate for the errors due to the
Yeah.
measuring instrument. Yeah.
Yes, that's precisely true. When we talk about pitot tube, you would see that we are having a correction factor to account for different kinds of intrusion that we really bring into the system when we measure, and these are basically dumped into a correction coefficient. Yes, you're right.
Got it, sir. Just another query.
Yeah.
This example, it is little bit tricky for me to understand, so that's the reason why I'm trying to ask this.
Yeah.
So, if I'm actually measuring the wear of a brake disc,
okay,
using a probe, which will actually touch on the surface of the brake disc,
Mhm.
it will be able to tell whether the the profile has changed drastically or whether because I'll know whether on the surface of the brake disc whether the surface is uniform because I'll be touching at all the points
Yeah.
of the surface of the brake disc.
Got it.
So, but I'm touching and measuring. So, do I call it an intrusive method or a non-intrusive method?
Okay, so if the touch is not really modifying the, it is not really wearing down the brake further, right, than what it is really, then it is a non-intrusive method. But if it is not, then it's a non-intrusive. So already the wear has happened because of rubbing, coming out of some actual use, right? And now you have put in a probe touching the surface. That touch should not really alter the level of, let's say, roughness or the surface properties. Then it is non-intrusive. But if it is really affecting the wear and affecting the surface property, then you need to be careful.
Noted, sir. Thank you.
I mean, you got the point?
Yeah, very clear, sir. Very clear. Yeah.
So this accounts for tolerances also, like let's say minor wear and tear, which is unavoidable, something like that.
Yeah, so I mean, see, of course, I mean, it's all relative, I would say, right? You have, let's say, I mean, I don't know how you characterize based on the surface roughness or, I mean, some kind of surface property, right? So, of course, any measurement, I mean, you would have tolerances. You have to define plus minus. But by putting in that method, whatever effect you basically incur should be negligible as compared to what the value is as compared to what the tolerances are, right? So the influence has to be very, very small. I mean, even smaller than the tolerances.
So just one thing I want to understand it clearly, that suppose in the case of pitot tube that you have given,
yeah,
if the diameter of the pipe is maybe 100 meter, for timing I'm telling you.
Mm.
So the measurement whatever error will be very small in that sense.
Yeah,
But
yeah, that is
suppose,
the point. That is the whole point. So,
but suppose the diameter is 10 meter, then the error will be very high. So
Yeah.
same experiment can be non-intrusive and intrusive based on
that's
situations,
precisely
right?
the point that I'm trying to make. Yeah.
Okay.
Yeah, the same
Thanks.
same experiment, depending on the probe and the experiment, you can say that, okay, it is intrusive in one case, in non-intrusive in another case. The same pitot tube can be treated as intrusive in one case, non-intrusive in another case, as you said.
Right, so got it fully. Thank you so much.
So why we are talking about intrusive, non-intrusive? Because we want to be careful that what we have measured needs correction or not. Okay.
Right, sir. Right, sir.
Okay, so if no further question, thank you, and we'll meet again tomorrow 6 p.m.
Thank you, sir.
Thank you, sir.
Thank you very much, sir.
Thank you,
Thanks a
sir.
lot, sir.
Thank you, 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 Professor.
Thank you.